So let's try out this example. So we want to evaluate the surfacing integral y plus z ds, where s is a surface whose side is a cylinder, x squared plus y squared equals 3. The bottom is a disk, x squared plus y squared is less than or equal to 3 in the x plane. And the top is the plane z equals 4 minus y. So let's go ahead and draw this region. So we got x, y, z. So the first thing that I see is that you got the cylinder, x squared plus y squared equals 3. And also the bottom is the disk, x squared plus y squared is less than or equal to 3. So on the xy plane, I actually have a circle of radius square root of 3. Then I have a cylinder going upward, wrapping around the z-axis. And then I got this plane z equals 4 minus y. If I let my y equals 0, I see that z equals 4. And then if I let my z equals 0, I see that y equals 4 as well. So that means this plane is going downward this way. So it's kind of slanting. It's kind of breaking up this particular can. So we kind of have something that looks like this. Okay. So if I say y plus z is my density of this particular shape, I just want to make sure that I know what the mass of this whole thing is. Alright. Now this problem is a doozy because there's 3 different components to this. There's 3 different surfaces, right? So I have surface 1, which I think will be our most complicated one. It's our cylinder. It's going to be our first surface. Then you also have surface 2. And that guy is going to be our plane, which is going to be our next part. And then you got surface 3, which is the bottom of the cylinder. So the bottom, I'm just going to write bottom circle. Okay, so you got all of that in here. So one of the things that we have to be very careful with, and let me go ahead and just maybe write down the equation. So the cylinder is x squared plus y squared equals 3. Our plane is z equals 4 minus y. And then the other guy is going to be x squared plus y squared is less than or equal to 3. Here, basically, z is equal to 0. That's kind of like another way that you can think about it. All right. So now the only thing that we really have to be very careful with is that there's 3 different surfaces that we got to deal with. So, and all of them are, and it's not just one function like it was, I'm sorry, it's not just one surface like it was before with a plane. Now we got to deal with 3 of them separately. So that means this problem is going to be terrible because you got to do 3 surface integrals. Okay. So let's go ahead and just start it. So, and the first thing is probably going to be the worst one, because we got to deal with this cylinder, okay? The bad part about the cylinder is that even though its parametrization may be, well, yeah, no, it's actually this parametrization. So if you look at the cylinder, if you remember to parameterize this, we're going to use x equals r cosine theta, y equals r sine theta, and then we're just going to let z equals z, okay? So now our parametrization is this. We need to figure out what r is. So in this case, our r is going to be square root of 3 because that's the cylinder. So we're going to have x is equal to square root of 3 cosine theta. Y is going to be equal to square root of 3 sine theta. And then z is just equal to z. Okay, so if you kind of want to think about it in terms of r, so we have theta and z, so those are our 2 parameters. And we got square root of 3 cosine theta, square root of 3 sine theta, and then z. So those are our parameters. Now, one of the things that kind of just sucks about this problem is that not everything is in x, y, z. So we can't use our formula like we did before. It wasn't a simple parameterization. So we actually have to use this cross product. So we have to take our partial derivatives with the 2 parameters, take the cross product, and then take its magnitude, and then plug it into the function. So that's what makes this problem a little more complex. So this one, we couldn't use the other formula because it wasn't a straight up problem this way, like that. Okay, so let's go ahead and take its cross product. So we're going to take the partial of theta cross with the partial of z. Okay, so I'm going to have, so this is equal to I hat, j hat, k hat. Okay, so the partial with respect to theta is going to be, so for the first component, it's going to be negative square root sine theta. Partial of j is going to be square root of cosine theta. This guy doesn't have a theta, so it's going to be 0. Then with respect to z, you can see that these two are going to be 0, and the last one's going to be 1. So then I'm going to have I hat is square root of 3 cosine theta 0, 0, 1 minus j hat is going to be negative square root of 3 sine theta 0, 0, 1. And then plus k hat is going to be negative square root of 3 sine theta square root of 3 cosine theta 0, 0. Which actually this is going to go away because when I take the cross, when I multiply out the diagonals, this is going to go away. So all I'm really left with, so this guy is gone. I just have the square root of 3 cosine theta I hat. And then the negative and the negative turn into a positive square root of 3 sine theta j hat. And now finally, all we got to do is take its magnitude. So the magnitude of this guy is going to be the square root of the sum of squares. So you can see that sine, cosine, and sine are going to go to 1. I'm going to get the square root of 3 squared. That gives me square root of 3. I'm sorry, that's going to give me 3. And then I take the square root again, so I'm just going to get square root of 3 back. So that's going to be the cross product. So that's going to be the number that I'm going to multiply this whole thing by. So let's go ahead and set up our surface integral then. Okay, so our surface integral is y plus z ds. Okay, so let's write that down. So this is for surface 1. So it's over surface 1, okay, y plus z ds, okay, because that's what it was. Okay, so this guy, so I'm going to say ds1. Okay, so this guy is just going to be equal to, so now what I'm going to plug in is going to be the square root. So I'm going to put the double integral. Okay, and then y plus z. Okay, so now we got to think about what y is. So y in this case is going to be, let's look at the parameterization here. So our x, our y, and our z. So our y is square root of 3 sine theta. And then our z is just going to be the regular z. So it's going to be plus z. We're going to multiply this by the cross product, the magnitude square root of 3. Okay, and then it's going to be over the region dA. Okay, so I'm just using, again, this formula up here. This guy. So I plugged in the parameterization, and I'm multiplying it by the magnitude. So that's how I got that. All right, so now let's take a look at the actual surface itself, or the region itself. So you can see that the region is going to be the following. So we gotta take, so let's take a look at the region. So the region in this case is a cylinder, right? The x squared plus y squared equals 3. Okay, so you can kind of take a look at this thing. So this inside of the cylinder. So you can see that this guy goes from 0. So let's look at the z values, because you can tell we need to figure out what exact our two parameters is z and theta. Now theta is easy because it's 0 to 2 pi. But z, you can see z starts from 0 and goes all the way to this plane. So z starts from 0 and goes all the way to the plane 4 minus y. 4 minus y. But we know what y is. Y is just a square root of 3 sine theta. So when we do that, this guy is just going to be equal to the integral from 0 to 2 pi, the integral from 0 to 4 minus square root of 3 sine theta, Then we're going to have square root. Okay, so I'm going to multiply the square root of 3 inside. That's going to give me 3 sine theta. And then I'm going to get plus square root of 3 times z. And then dA, so this is going to be dz first, and then after that d theta. Okay, I'm just going to make sure that I did that right and checking. Okay. Okay, so now what I'm going to do is let's go ahead and take the antiderivative of this guy. So I'm going to take the antiderivative with respect to z. So this guy is going to be equal to the integral from 0 to 2 pi. So it's going to be 3z sine theta plus square root of 3 over 2z squared from 0 to 4 minus square root of 3 sine theta d theta. Alright, so now this guy is going to be equal to, so I'm going to plug in the first guy, 0 to 2 pi, 3 times 4 minus square root of 3 sine theta, then another sine theta, plus square root of 3 over 2, 4 minus square root of 3 sine theta squared d theta. Okay, so what is this going to give me? So this guy is going to give me 0 to 2 pi, so I'm going to get 12. So the first one's 12 sine theta, so I'm just taking these guys. And then the other one will be minus 3 square root of 3 sine squared theta. Then I'm going to have square root of 3 over 2. And then in the inside, oh gosh, okay, 16 plus, no, that's the minus 4 square root of 3, that's going to be 8 square root of 3 sine theta plus 3 sine squared theta. Okay, so this is going to give me 0 to 2 pi. 12 sine theta minus 3 square root of 3 sine squared theta. So this is going to give me 8 square root of 3. The other one's going to give me, so this is going to give me a 4 times 3. That gives me 12 sine theta. And then the last one's going to give me plus 3 square root of 3 over 2 sine squared theta, d theta. Okay. Alright, so I do see a couple things canceling out. So I do see this guy canceling out. Okay, and then this guy, so I do have an 8 square root of 3 here. And then I'm going to have, what is this? So it's going to be minus 3 plus 3 halves. Negative 2 halves square root of 3. Okay, so negative 2 square root of 3 sine squared theta. Alright, and now we're going to take, oh gosh, okay, so now we got that sine squared theta that we got to get rid of. So we're going to use a half angle identity. 0 to 2 pi. 8 square root of 3 minus 3 square root of 3 over 2. That guy is going to be 1 half 1 minus cosine 2 theta. Okay. So now I'm going to have integral from 0 to 2 pi 8 square root of 3. So this is going to be minus 3 square root of 3 over 4 plus 3 square root of 3 over 2 cosine 2 theta. Oh gosh, okay, I think I got it. Okay, and now I'm going to have that 8 minus 3/4. That's going to give me 29 over 4. Okay, so 29 over 4. square root of 3, and then plus 3 square root of 3 over 2 cosine 2 theta, d theta. Okay, now let's take the antiderivative with respect to theta. So that's going to be 29 square root of 3 over 4 theta. And this guy is just going to give me a 3 square root of 3 over 2. Antiderivative, that's 1/2 sine of 2 theta from 0 to 2 pi. You can see that basically this next thing is going to go away, so you just get 29 square root of 3 over 4. Okay, and then this should be with pi, I think, times 2 pi. Just 29 square root of 3 over 2 pi. Whew, oh my god, that was a lot. Okay, so that is only the first surface integral. So this one was the most horrific one. The other ones are a little bit easier. Okay, so now let's do the plane. So the entire mass on the cylinder, S1, is going to be this 29 square root of 3 over 2 pi. All right, now let's go ahead and figure out our next one, which is going to be our plane. So our plane, so S2, our plane, we got to go ahead and parameterize it. Now this one's an easy one, so we don't have to use a cross product anymore. So we're going to let x equal x. We're going to let y equal y and z equals z minus y, 4 minus y. So we can kind of think of r of x comma y is just going to be x, y, and 4 minus y. All right, so now luckily for us, this one we don't need to take the cross product. We can just use our regular surface integral formula. So we can just do the double integral over the surface 2 of f of x comma y comma z ds. So we're going to take our double integral over the region D. So we know it's y plus z, but we know what z is. Z is 4 plus minus y. We're going to multiply this by the square root of the derivatives, right? So in this case, we're going to look at the f sub x and f sub y. F sub x is just 1. Okay. No, wait. Because we're looking at x and y. Looking at this one, this is g. So we're going to take the derivative with respect to x, that's 0. And then the derivative with respect to y, that's -1. And then plus 1. Okay, over the region, over dA. So this goes away. Here we're going to get square root of 2. So we get 4 square root of 2 dA. Okay, and now we got to think about what exactly is going to be my limits of integration. Okay, so if you look at it, so let's look at the region, and this is with respect to x and y. So if you look at the region itself, the region of this plane is going to be this circular part. Which if you go down, that's just a circle, right? It's a circle that was given to us by this cylinder. So the circle radius is square root of 3, right? All around. So basically we can just convert this guy to polar. So we can just convert this to the double integral. It's 4 square root of 3. Change dA to r dr d theta. We know that our radius is from 0 to square root of 3, and then from 0 to 2 pi. Alright, so we're going to get 4 square root of 2. I'm in the margin now. Integral from 0 to 2 pi. This is going to be r squared over 2 from 0 to square root of 3 d theta. So this is going to be 4 square root of 2. And that's going to be 3. Yeah, this is just going to be 3. Oops, wait, I messed up. It should be square root of 3. Oh, wait. There's a 2 here. There's a 2 here. And then there's a 3 there. Okay, I think I got it now. Okay, so then this guy, plug that in. We're just going to get 4 square root of 2. Integral from 0 to 2 pi. 3/2 d theta. I'm going to take that out. So you're going to get the 2, so 6 square root of 2, and then times 2 pi, which gives me 12 square root of 2 times pi. Okay. All right, and then our last one, which is S3, and that's just the bottom part. Okay, so the bottom disk. And notice that the equation of this bottom disk is just z equals 0, right? So this x squared plus y squared is less than or equal to 3. That's just in the xy plane. That's just z equals 0. So the bottom part is going to be z equals 0. And then you can just let x and y be just x and y. Okay, so our x comma y is going to be just x, y, and then 0. So now the double integral over the region, over the third region, y plus z ds. Again, this looks like a simple one. So we know z is 0, so we're going to do double integral over the region d. Y, z is 0, and then you're going to get the square root. Since z is 0, that means all of our partial derivatives are 0. So we're going to get double integral over the region d of just y dA. And then because we're looking at our at a circle of radius square root of 3, we're going to convert to polar again. So this guy's the double integral from 0 to square root of 3, and then 0 to 2 pi. This guy's going to be r sine theta. R d theta, so it's r squared d r d theta. And now to kind of just think about it before you even start doing all the integration, you can notice sine here. So this guy is going to have a value, but if you look at sine is being evaluated from 0 to 2 pi. These guys are going to end up canceling each other out. So you end up actually getting 0 for this guy. Okay. So that means our total mass, so our answer, is going to be equal to 29 square root of 3 pi over 2 plus 12 square root of 2 pi. And now this problem is finally done. So even though I almost messed it up towards the end. But yes, this is probably one of the most complicated problems that you'll see, but it combines everything together. And yeah, this problem is absolutely horrific.